Hi, my name's Jim Shepik, and my project focused on improving TikTok retrieval. If you're not already familiar with TikTok, it's a social media platform for short-form video content. There's an emphasis on music. A lot of the content is people lip-syncing or dancing to popular songs, and it's one of the most popular social media platforms today. When you run a search on TikTok, there are really two categories that it could fall into. Either you're searching for videos related to a topic or trend, which oftentimes works pretty well, or you're trying to find a specific video. If you've used TikTok, you know that feeling of when you've got a TikTok in the back of your mind that you're trying to find, you search through all of your liked videos, and you just can't find it. That's what I'm trying to improve with this project. Those searches that have a single target, trying to find a single specific TikTok. There are a few quirks of TikToks that make them particularly elusive when it comes to retrieval. First, by their short nature, they're just naturally harder to find. Shorter video means fewer keywords. Additionally, the description text is often not that helpful. A lot of times it's used like just to make the punchline of a joke, or it's filled with really popular hashtags that don't narrow things down when you try to search for them. Another challenge is that the most important information in a TikTok is actually in the video itself, so it's not natively in text format. Additionally, a lot of content is sort of non-verbal or subtextual or referential, which is really challenging for retrieval. And finally, I did a search and I couldn't find any public information retrieval literature on TikTok, so best practices are not really well known. The TikTok I'm about to show highlights some of these challenges. The descriptive text is really short, and it's not actually that useful at all, and the content is purely visual. Let's talk a little bit about normalization. I decided to keep the @ sign, which is used to designate user handles, and the pound sign, which is used to designate hashtags. I used these two packages called Unidecode, which convert emojis into English rather than deleting them, because as you can see in this example on the right, sometimes the emojis are part of the content, and which will convert sort of weirdly formatted letters into normal ASCII letters. In terms of actual experimentation, I decided to test n-gram tokenization versus word tokenization. My hypothesis was that short n-grams, like 4 grams or 5 grams, would be the best, partially because I'm not using any stemming with word tokenization, and typical English language word stems are, around 4 or 5 characters long, and because there are a lot of typos on TikTok, and hopefully, short n-grams can kind of get around that. The next thing I wanted to look at is if we can improve the retrieval performance by enriching the basic username, description, music title information with extra text. So we're going to look at 3 different sources of text. First is top comments, which could be really useful, especially for videos that are mostly visual in nature. But if there are a lot of off-topic or unrelated comments in the descriptions, then they could result in more irrelevant retrievals. The next source we're going to look at is text extracted from the video itself using speech recognition. I figured that since the video is kind of the main vessel for information, then whenever we can get things with speech recognition, they'll always be useful. TikTok actually does speech recognition itself to generate captions, but I wasn't able to scrape this information, so I had to use a Python package, and the results were not as good. The last source we'll look at is text extracted from optical character recognition on cover photos. Sometimes cover photos contain like the title of a video or a question that the creator is responding to, but sometimes if the video just has a block of text that's visible in the first frame, that becomes the cover. Either way, I figured that OCR text would always be useful if we have it. Next, I want to look at attributing fields, or labeling the terms based on which feature they came from. If there do happen to be a lot of irrelevant documents retrieved because of off-topic comments, this should kind of help fight against that. Finally, I wanted to optimize the formula that we use for computing document vectors in the cosine scoring process. Because the average TikTok is, like less than 10 seconds, I have a feeling that binary term weighting will be the best. In terms of collection frequency, not all words are equally useful as keywords, so I think that either IDF or probabilistic IDF will be better than no collection frequency weighting. In terms of normalization, I think we'll be better off without it because it may end up actually penalizing documents that have more enriching text. So to sum up, I think that what's important is what keywords are there and how useful are they, not how often they occur and not how much other text there is. To acquire the corpus that I needed to answer all these questions, I wrote a program in JavaScript that scraped information off of TikTok. Notably, instead of getting all the comments, it just got whichever ones were loaded, which usually happened to be about 20, and they weren't always in order of, popularity or likes or whatever, and sometimes it missed the comments altogether. A lot of the videos got corrupted during the download process, so I just threw those ones out. In terms of speech recognition and optical character recognition, I used Google Speech and PyTesseract pretty much just out of the box. I really didn't do any quality assurance other than like a spot check that it worked for like one example. And the corpus does have some Japanese in it because that's my second language. And I didn't do any language labeling whatsoever, so hopefully the speech recognition and OCR were able to figure it out. Here's a screenshot from TikTok's desktop site. Pretty much all of the fields of information that you can see here are what my scraper was able to get. Because we're focusing on improving search when there's only a single target, it doesn't really make sense to use precision or recall to measure our performance, so instead we're going to look a lot at the rank of the single target. Whenever targets fail to be found by our retrieval technique, we'll interpolate those missing values with 731, which is the midpoint between rank number 1 and last rank. The queries were generated by 11 of my friends and I. There are 86 test queries in all. We pretty much watched a bunch of videos in the corpus, picked a handful that we liked, and came up with queries that we would use to search for them. I hacked together a PHP page for my viewers to use to watch the videos in the corpus, just to kind of streamline the process a little bit. It's got most of the information that you could see on TikTok itself. I even implemented a rudimentary ranked search algorithm in JavaScript, which is kind of painful, but hopefully it made it a little bit easier for my participants to go back and find the IDs of the relevant targets. Once I had all the queries in hand, I ran the experiments, and now I'm going to show you the results. I focused on individual queries, and I looked at how the rank of their single target was distributed over all of the experiments that I ran. I picked Josh's queries to show you as an example because they really highlight the 3 different types of queries that we saw. First, there are the best case queries, which have a mode around 1. This means that in most experiments, they were retrieved and ranked pretty highly. Then there are the average case or challenging queries, which have 2 modes, one around 1 and one around 731, meaning that depending on the experimental methodology, sometimes they could be ranked pretty highly and sometimes they could be missed altogether. And then there are the worst case queries, which only have a mode around 731, meaning that most of the time they were missed. Out of all 86 queries, only 4 of them were bad, so I just decided to treat these as outliers for the rest of our analysis. I took a look at how performance was related to query length and didn't really see a strong trend. I went through and watched all of the query targets and I manually labeled them with these 5 attributes. If you want to take a look at the criteria that I used to make the judgment, you can go ahead and pause the video and read the slide right now. I wanted to understand how retrieval performance was related not only to the retrieval methodology that was used, but also to the properties of the targets themselves. These figures show that the biggest improvement in rank is correlated with videos that have useful descriptions or comments that are on topic and contain a lot of keywords, whereas the biggest degradation in rank is correlated with videos that are purely visual and have no dialogue or narration. The results that we see for document vector formulas are pretty much exactly what we expected that they would be. Normalization is strongly detrimental to the median target rank, and binary term weighting is present in all of the best formulas. Probabilistic inverse document frequency is the best choice for collection frequency term. Now let's take a look at how the retrieval performance was affected by the inclusion of extra text sources. The first conclusion that we draw from this chart is that any source of extra text provides better results than none. Second, if we only had to pick one, the best is actually top comments, which we didn't predict. And top comments alone are so good that speech recognition and cover photo OCR together are about equal in performance. But using all 3 extra sources provides the best results. Looking now at tokenization method, we see that our hypothesis was largely supported. Word tokenization failed to rank the relevant target nearly 3 to 4 times as often as 5 gram or 4 gram respectively. When we cross tokenization and extra text sources, we see that 4 grams tend to optimize towards better recall with a lower miss rate, especially when there are fewer included features. On the other hand, 5 grams tend to optimize towards better precision. They're more likely to miss some keywords, but when there's enough text, the average rank is closer to the top of the list. Looking at field attributions over our best indexes, we can see that they actually ended up hurting performance. I guess this means that it doesn't really matter where the keywords come from as long as they're there. So using field attributions really only serve to screw up the IDF calculations. Using these conditions, we were able to find the correct TikTok and put it at the top of the ranked list 66% of the time, over double what we were able to do using all of the best conditions but only the basic text. Additionally, 90% of the time the correct TikTok was in the top 8, whereas this was only true about 51% of the time if we didn't use the additional text features. In conclusion, most of our hypotheses were supported. The one result that was kind of surprising is that out of the 3 extra text sources, top comments were actually the most useful, and they were more useful on their own than speech recognition and OCR were together. This is actually pretty good news for TikTok, since comments are a lot easier to obtain than speech recognition and OCR, which you kind of have to put in some more computational legwork to extract. I had expected comments to be a little bit lower quality because they can be spammy and off topic, but it's not as if off topic comments are on topic to other TikToks. And in terms of spamminess, we discussed with the document weighting scheme that it doesn't really matter what other text we include. It's just about, are the keywords there and how useful are the keywords? I've got a lot of ideas about different ways to proceed from here. TikTok really has a lot of untapped potential as a source of interesting challenges for information retrieval. This was a really fun project to work on, so if any of you out there in the audience happen to be in touch with any hiring managers at TikTok, maybe forward them my contact information. Finally, I gotta give credit where credit is due. Special thanks to my dad for providing me with a VPN service. Without it, I would have been IP banned from TikTok, and I wouldn't have even had a corpus to do experiments on. Thank you to all the query authors. You really helped out. Sam, Joe, Josh, Nick, Emily, Jack, Huey, Geneva, Grove, Charlie, and Anvesha. Without you, I would have written all the queries myself, and the results would definitely have a lot of researcher bias in them. And last but not least, the content creators whose data I helped myself to. Without you, there would be no project at all. So thanks. I hope you all enjoyed the presentation, and that's it, I guess.